Okay, good morning. My name is Cesar Morgado and I will start my presentation. The title is Where Study of Innovative Titanium Tantalum Allows. I will start with motivation of this work, then I will pass to introduction. I will talk a little about laser cladding, I will talk a little about the equipment, the automation of the process, the fabrication of titanium tantalum alloys, experimental procedures, preparation of samples, Young's models and hardness determination, wear tests, then I will talk about the results and the discussion, and at the end, the conclusions. This work was motivated by the continuous demand of biomedical industry, remains the need to innovate in new alloys that fulfill requirements like cut plate stiffness, strength, fatigue, wear and corrosion resistance, and of course biocompatibility. The recent years, efforts are being made to develop new titanium alloys using non-toxic elements such niobium, tantalum, zircon, and molybdenum. There is a scientific interest of characterizing the wear behavior of these innovative titanium tantalum alloys, once that is not studied and consequently not documented. Wear is a common form of material degradation that can occur during extended periods of service, and if unchecked can significantly impair structural integrity. Wear is a progressive phenomenon, and failures due to the wear are generally encountered in the last quarter of the component life. The focus of the present work is the study of the wear behavior of titanium 30% of tantalum and titanium 52% of tantalum innovative alloys. These alloys were produced by laser cladding in the Institute Superior Technique of Lisbon University in Portugal, of course. Laser cladding is a technique to enhance the surface protecting by addition thin clads of similar or dissimilar material. This process will increase surface mechanical properties as hardness, wear, and corrosion resistance in mechanical components, subject to adverse working conditions such as aggressive environment, thermal cycles, and so on. It also increases lifetime of the mechanical components. Here we can see the equipments for laser cladding. We have laser, 3 linear guides, nozzle, powder feeder, chamber, or glove box. The needs of control parameters are as overlapping, number of clads, deposition rate, laser power, and powder feeder rate are very important in the process and influence the mechanical properties and durability of the coatings. In figure is showed the control scheme of the laser cladding equipment controlled by a personal computer. With the automation of the process is possible with only one program control and define all the parameters of the process and of the equipment, and obtain different chemical composition in one sample, keeping the same process control parameters, varying linearly the mass flow rate from two metallic materials in synchronization with translation movement of Chi table. For addition of metallic powders to the molten pool was implemented a lateral nozzle configuration. Through 2 linear guides, the incidence of powders flowed the molten pool in position in X and I. The angle of incidence of the powders flow can be adjusted with the position. If the control of the powder feeder is also used, it was used a controller, a Arduino, a drive, a DAC, and a POP, as shown in figure. This controller received control instructions through the USB from the control programs. The laser is a fiber laser that can be controlled by RS232 interface, as shown in figure, dropped configuration and control commands defined by the fabricator. In order to define that the laser receives the command sense, the laser generates a response which consists in an echoed back command. So, preparation of the alloys. A plate of commercial poor grade 2 titanium was used as substrate. Prior to the position of the substrates were sandblasted and cleaned in alcohol in an ultrasonic bed. We used two powders, poor titanium and poor tantalum. The mixture of powders is done in a turbo mixer during 45 minutes. The powders were mixed at 100 degrees Celsius during 24 hours. Due to the high reactivity of the titanium with oxygen and nitrogen at high temperature, that often lead to embrittlement, the deposition process was carried out in the chamber under controlled argon atmosphere to avoid contamination. 18 mm long track have been produced in two ranging of nominal composition. One ranging from poor titanium to titanium 30% of tantalum, and the other ranging for titanium 30% of tantalum to titanium 90% of tantalum. The laser cladding experiments were carried out using a ND-YAC laser beam power of 2 kilowatts, continuous wave at a scanning speed of 5 millimeters per second. The surface of the track were metallographic polish and etched in chrome reagents. The composition of the alloys was measured along the track's length by ADS microanalysis. The microstructure of the tracks are characterized in detail by optical and scanning electron microscope. The micro hardness and Young models of the samples were measured by depth sensor ultra micro indentation tests. The Young's models characterization. There is a significant decrease in values of these elastic models from 120 to about 50 gigapascal, with increase in tantalum contents in the alloys from 3% to about 30%, as can be seen in figure. Young's models values for alloys with tantalum contents in the range of 65, presenting very low stiffness formed in this region. And extremely low values of Young models, 32 gigapascal, has been measured for the titanium 52% tantalum alloy. The Young's models, they remain relatively constant in values about 50 and 55 gigapascal up to 65% of tantalum. For higher tantalum concentrations, the Young's models increase again up to the maximum value of 90 gigapascal for the 86 tantalum ones. The hardness. There is an initial fast increase in hardness of the titanium tantalum alloys from 1.7 to 2.2 gigapascal, during to an increase in tantalum contents from 0 to about 30%. The hardness values increase to 2.3 gigapascal for alloys with 30-35% of tantalum, and then decrease again for alloys between 45 and 55%. For tantalum contents about 55% of the hardness increase again up to 2.4 gigapascal, again with solid solution strengths. Microscale reservoir tests use the Flint TA66. It is a fixed ball system with the microscale reservoir. Titanium 30% of tantalum and titanium 52% of tantalum samples were tested, and the balls used were the steel and have 25 millimeters of diameter. In table 1 are present the Young's models and the indentation hardness of the balls and the samples. For all tests, the normal Modulus was 1 Newton. The linear speed was of 0.2 meters per second. The angular velocity of the ball was 16 radians per second, and the duration of the one rotation was 0.393 seconds. After the microscale abrasive wear test, the criteria produced in the samples were observed in an optical microscope and was possible to measure the radius R. Crater diameters increasing with the increasing of the number of the rotation of the ball. This occurred due to the fact that by increasing the number of the rotation for a constant velocity of 0.2 meters per second, increase the time test and consequently the sliding distance. In figure 22 can be observed that the titanium 52% of tantal crater diameters are bigger than titanium 30% of tantal. This fact occurs because the hardness of the two alloys is different, but very close. Of the analysis of the table 2 and 3, it's noted that the titanium 52% of tantal alloy present higher values of wear volume and wear coefficients than the values of titanium 30% of tantal. From figure 23 can be observed that the wear coefficient does not vary linearly with the rotation of the sphere test. The wear coefficient is lower for the alloy with the higher hardness. The coefficient increases up to 300 rotation per minute and then begin to decrease. In figure 24, 25, and 26 present the evolution of the wear volume in function of ball test rotation, sliding distance, and time test. Observing the three graphs, linear dependence is observed, which indicates that was being reached the steady state wear. Can be observed that wear volume is not a material property, since it varies with the test conditions. For conclusions, with the present study, it was concluded that the innovative titanium 30% of tantal and titanium 15% of tantal alloys have wear behavior very similar. The wear coefficient is lower for the alloys with higher hardness. Wear coefficient does not vary linear with the rotation of the sphere test. The coefficient increases up to 300 rotation per minute and begins to decrease. This decrease occurs because 300 rotation per minute, the particles are released by the sample and are deposited in the contact between the ball and the sample, which leads to a decrease in the coefficients of yield. The analysis of the ball criteria shows that there is a just growing abrasive and the volume wear abrasive is higher for the lower hardness alloy, although the hardness of titanium 30% of tantal and titanium 52% of tantal are very approximate. As both alloys have low Young's models, they can be used in biomedical application. However, the titanium 52 tantal presents the wear behavior more compatible with what is expected for the develop new implants alloys. Doctors would like to thank the Portuguese Foundation for Science and Technology and to the Lisbon University and to New Lisbon University. Thank you very much for your attention.
Thank you.